going to tell you about how Stardust, the outputs, can actually be applied within exoplanetary science. And also, because I'm at the University of Warwick, we actually have a space debris program here called Debris Watch, where we actually are monitoring some geosynchronous space debris. And I felt like I should speak about that a little bit given the audience and also given Detlev's talk earlier. So I'll have a few slides at the end for that. But the main thrust of this talk is actually going to be to relate Stardust to exoplanetary science. And we do that in two ways. We do it through asteroids, and we do it through dynamics. And asteroids, there are many processes on these asteroids which are actually relevant for exoplanetary science. These include evolutionary processes, such as erosion and also thermal fracturing, perturbations on asteroids. These include gravitational perturbations and non-gravitational perturbations, various size distributions in different reservoirs, including the main belt and the Kuiper belt and the Trojans. Also, the escape rate of various asteroids. This is from resonances due to something like the Yarkovsky effect, and also the transfer of different amounts of asteroids from between different reservoirs, such as the Centaurs, Kuiper belt, even the Oort cloud, and the main belt. And in terms of dynamics, one particularly important aspect is to consider highly eccentric bodies, because I'll show you why this is particularly important for these extrasolar asteroids. And also chaotic and resonant dynamics, which is very important for solar system asteroids as well as for extrasolar asteroids. Now, we actually have discovered specific exoasteroids, but they're not where you might think they are. They don't orbit stars like the sun. At least they do orbit stars like the sun, we just can't see them. And we also can't see them around giant branch stars. Instead, we see them around these dying stars known as white dwarfs. And these white dwarfs have particular properties that enable us to actually determine, to detect these asteroids. And these white dwarfs effectively are dying stars. They're the endpoint of stellar evolution. So they, can you still hear me?
Yes.
Yeah.
Oh, okay. Oh, okay. Sorry.
But okay, in your screen, maybe you can go to the full mode presentation because. Okay.
Can you?
Now, yes. Now it's working. Your full mode presentation.
Oh, okay.
Full screen.
Okay.
Sorry, presentation.
Okay. Thanks. So yes. So these white dwarfs are the endpoint of stellar evolution, and our sun is going to become one of these white dwarfs. And actually, the reason why we can detect exoasteroids around white dwarfs partly is because they're so compact and they're so dense. They're very similar to the Earth in size. As you can see here, the white dwarf is actually 5 orders of magnitude higher surface density, so it's extremely dense. And as a result, all of the elements in the atmosphere sink very quickly except for hydrogen and helium. So any asteroids that are actually deposited onto the white dwarf can be detected, and very easily, in fact, because they stand out very clearly amongst this blank slate of hydrogen and helium. And because these white dwarfs are so small, that we can actually detect transits of these asteroids that break up around the white dwarf quite easily. And the reason is because the dust and the gas that's produced from asteroids which break up, actually they can cover a high fraction of the white dwarf. They can actually block nearly half of the flux from the white dwarf. And the first of these exoasteroids that was discovered in 2015 was found through this way, through transit photometry. So what you see here is a plot from that original paper, and you see here a photometric transit depth of 40%. which is actually very striking because in exoplanetary science, when we look for exoplanets, we're looking for a transit depth of only 1% or maybe 0.1%. So 40% is quite striking. And the other aspect about this exoasteroid is that it's probably breaking up. And this can be determined from the character of this transit curve. If the asteroid was a solid body, it would follow the red curve. But because it follows the blue curve, we're actually probably seeing a dust cloud that's generated from this asteroid. Now, there have been at least 20 follow-up papers for this system, and we've obtained much better photometry from the discovery paper. And this is just one of many examples that I can show you. The asteroid is thought to be on an orbit that's 4.5 hours. So it's right at the Roche radius, right at the disruption radius of the white dwarf. And I just put this image of 67P up here to show you that, to just illustrate that we think it's breaking up, we think it's sublimating, and we think it's tidally disrupting at the same time. And this curve gives you an indication of just how intricate the structure is. You can see various ingresses and egresses, and the numbers and the letters, they all refer to features that repeat over different time scales. Some of these features repeat over weekly time scales, some over monthly time scales, and some over yearly time scales. So in fact, since 2015, this asteroid has been disrupting because this curve changes constantly. And a good example of this is one paper where you can see 4 different transit curves, each from 4 consecutive weeks in 2017. And just over the course of a week, the main transit feature, as you can see here, actually changes the depth of this curve by 10 to 20%. So the system is very dynamically active. At least it was during this month in 2017. And sometimes it goes through quiet periods, sometimes it goes through more excited periods. And I'll just show you one more of these curves. This is from 2018. I don't remember which week or which month. But here you can see a very long transit feature. This one lasts for about for 50 minutes. And one can try to construct models to explain this, which can be difficult because there's degeneracies here. Can we explain this by overlapping dust clouds, or can we explain this by several fragments that are in a co-orbital configuration, all that have been broken up from this asteroid? There have been a few attempts to model the evolution here, and I'll show you a movie now of one of these attempts. This is one where we use the PKD-grav code, which is often used in asteroid dynamics, and we considered how do we generate disruption over many years, because we need this disruption to last for many years. So what we did was we constructed an asteroid with a core and a mantle, and the core is much denser than the mantle, and we placed this just outside of the Roche radius of the core, but inside of the Roche radius of the mantle. And so what you see here, if you can see the movie, is that the asteroid becomes a lemon shape, and part of the mantle gets disrupted out of the L1 and L2 points. And by tweaking the orbital parameters, by tweaking the density and the eccentricity of the orbit, we were actually able to constrain what some of the parameters for this asteroid were. Now, the constraints were very basic because these transit curves are so complicated. And in a follow-up study, we actually considered a 3-layer model, one with a core, a mantle, and a crust. And we changed the densities of all of these structures. And as you can see here, as we change the density of the mantle to the core, the resulting transit feature does change. It actually becomes deeper as we increase the mantle to core density ratio. And also, we can, by increasing that ratio, we can detect differences in a broader phase range as well. Now, transits are not the only way to find these exoasteroids. In 2019, one of these exoasteroids was discovered through spectroscopy. And this one actually orbits with an orbital period of 123 minutes, which effectively is a record breaker, but it means it's so close to the star that it cannot be a rubble pile. It cannot be a main belt-like rubble pile. It must be purely metallic, and it must have some internal strength. So maybe this asteroid is really like a core of a progenitor planet or a progenitor large asteroid. And we also found that this asteroid is on a moderately eccentric orbit, but well within the Roche radius of a rubble pile. Now, those are individual discoveries, but what has driven this field actually over the last 10 or 15 years is that over 1,000 white dwarfs show evidence of asteroids being accreted onto their atmospheres. And we've now seen this in approximately 25 to 50% of the known Milky Way white dwarfs. And what's remarkable about this collection of 1,000 white dwarfs is that we can actually perform autopsies on these exoasteroids. So we can determine the relative chemical abundance of various elements. Because these white dwarfs are so dense, once an asteroid accretes onto it, it breaks up into its constituent atoms. And if you make assumptions about whether or not the secretion rate is in a steady state, you can compute the ratios of these chemical elements. And so we found 20 metals so far, and we found a wide variety. But in most cases, these exoasteroids are dry. They actually do resemble the bulk Earth, with high concentrations of the rock-forming elements magnesium, iron, silicon, and oxygen. There are a few fantastic exceptions which actually are water-rich. So there are a few cases where the progenitor asteroid was water by mass fraction of at least 40%. But most of these are actually dry. And then given how good these chemical constraints are, it's really the most direct way of actually probing the chemical composition of extrasolar planetary systems. Then we can create these geology ternary diagrams where you can quantify the amount of crustal, the amount of core, and the amount of mantle material that are on these asteroids. And by doing this, we can get a sense of how differentiated particular exoasteroids were. So we can really perform detailed comparative exoplanetology, but only through asteroids and by comparing it to various asteroids and meteorite classes within the solar system. So to help summarize this procedure, maybe I can just describe what's probably going to happen to the solar system. So when the sun becomes a giant branch star in about 6 billion years, violent changes will actually occur in our solar system. For one thing, the sun will increase in size by a factor of hundreds, and it will engulf Mercury and Venus. Now, Mars and the outer planets will all survive, whereas Earth is right in between. We actually don't know if it's going to be engulfed or survive. But arguably, the more interesting consequences are what happens to the minor planets in the solar system. Because when the sun becomes a giant branch star, it will increase its luminosity by a factor of thousands. And as a result, the Yorp and the Yarkovsky effects will be supercharged. And the asteroid belt, all asteroids effectively below 10 kilometers will probably be destroyed, although more work needs to be done on this. And even those above 10 kilometers might very well be susceptible to destruction. Some of these asteroids in the Kuiper belt will be destroyed by the supercharged Yorp effect, but in most cases, those will be moved around by the Yarkovsky effect. And when I say moved around, I don't mean a constant semi-major axis drift like that we normally apply to the Yarkovsky effect. Because the luminosity is so high, the eccentricity and the inclinations will change as well as the semi-major axis, and the semi-major axis won't change in a constant way. Then when the sun becomes a white dwarf, we'll have 5, maybe 6 planets that do survive, as well as a sea of debris, at least within the inner solar system, and many surviving minor planets in the outer solar system. And what we see in extrasolar systems is that these minor planets and this debris, they somehow make their way to the white dwarf. And how they do that has been the subject of many papers and still a lot of speculation. And this is where Stardust could really help, determining what mechanisms can provide the gravitational and non-gravitational perturbations to for all this debris to actually reach the white dwarf. And so there are 5 major questions for these exo-minor planets, and I'll go through each one of these. So the first one is, how do we formulate these transport networks for asteroids in different planetary architectures? Now, the solar system is, relatively speaking, very complicated compared to the known extrasolar systems. And these interplanetary transport networks, where we can transfer asteroids through different planets, different moons, and different asteroid reservoirs, has already developed quite a detailed formulation. And so the challenge is to simplify this, not too much, but a little bit, enough to help explain the observations in these extrasolar systems, which, as we know, in most cases just have a few planets and whose orbital architectures are largely unconstrained. We do actually know in the solar system right now that asteroids are perturbed toward the sun on a particular time scale over, due to different mechanisms. But in white dwarf systems, we have much better data over lots of time, over many different time scales to match this. Second question is, what resonant mechanisms create escape from different reservoirs of matter? So this is a plot of asteroid eccentricity versus the semi-major axis, the orbital period ratio of an asteroid, both before and after the sun undergoes this giant branch transition. Now, the solid lines here represent the typical libration width you would compute for a 2-to-1 resonance right now. And the dashed lines represent what that libration width looks like after the sun becomes a white dwarf. Because during this transition, the sun will lose about half of its mass. And in doing so, it'll actually expand the orbits of these asteroids. So their semi-major axis ratios will remain the same, but their stability boundaries won't. And as you see, the libration width does change of this resonance. And all these red squares here, they refer to asteroids which were disrupted during this transition and eventually were perturbed towards the white dwarf. So you can see in between the solid and the dashed lines, there are many asteroids here that effectively escape. Now, this study did not incorporate the Yarkovsky effect, but when one does, this resonant escape should be accelerated. The next question is, what is the dynamics of perturbed, highly eccentric orbits? And the reason why that's important is because all of the surviving planets and asteroids will be beyond a few AU. The sun will clear out when it becomes a white dwarf. It'll clear out all material within a few AU because it becomes so large. So for an asteroid to reach the white dwarf, it needs to achieve an eccentricity of at least 0.99. And so the dynamics of these highly eccentric orbits is very important in white dwarf systems. And we've been studying this to some moderate extent, and we've actually found some interesting results. And it turns out during each pericenter passage, the transfer of spin angular momentum and orbital angular momentum can create chaotic spin evolution, as you see in this plot. The y-axis here is the spin period over the mean motion, and this is over time. And because the spin is chaotic, the spin can actually increase to the point of breakup, depending on the specific orbital parameters of the system. And this chaotic spin evolution only is achieved for non-spherical objects. So this particular example shows a Proteus-shaped object. Also, we found some extremely high order resonances for these highly eccentric orbits on the order of 1,000 to 1 or 500 to 1, which you can see here in this Poincaré map. Next question is, how do erosional and radiative forces actually evolve these asteroids? It's quite
Sorry,
important.
you have almost 10 minutes left, including the time.
Okay, thanks, Adina. And so, yeah, so how do erosional and radiative forces actually evolve these asteroids? And this again deserves more study, and this, maybe Stardust can help inform us. This plot here is a plot from a paper I published with Dan Shears earlier this year that shows how various generations of Yorp failure. And so every black dot here represents an instance of Yorp failure, Yorp breakup, as the star is increasing its luminosity on its way to the white dwarf. So you see here 4 generations of breakup. At the first black dot, the asteroid breaks up into 2 child asteroids, or I think it's 6 in this case, and then at each successive one, another 6. But as the luminosity of the star increases, they spin up very quickly. And then as soon as the star becomes a white dwarf, then it levels off, because then the white dwarf's luminosity goes down very quickly, and then you're left with a sea of debris, 6 to the 4 particles. But we need to understand these processes better, and also the chemical evolution during these phases. And the last question here is, how do asteroids of different shapes and compositions break up? I showed you before the simple modeling we've done with a 2-layer sphere and a 3-layer sphere. But of course, asteroids are generally not spheres. And my PhD student, Katrina McDonald, has been working on disrupting asteroids of different triaxial shapes, both through impact onto the photosphere of the white dwarf, and through fragmentation, and through sublimation. So if you give Katrina, for example, a shape distribution as well as a size distribution of asteroids, then she'll be able to compute the various destruction characteristics as this belt moves towards the white dwarf. And so those are the 5 questions, but in the last few minutes, I just want to shift gears entirely and quickly talk about this debris watch program that we have at the University of Warwick in collaboration with DSTL, which is the Defense Science and Technology Laboratory, a government laboratory in the UK. There are many people involved, but PhD student James Blake, who is a participant at this conference, has led a paper which is now published in Advances in Space Research. And the thrust of the program is to look for faint geosynchronous debris. There are no natural removal mechanisms at GEO. And as a result, objects which are less than 50 centimeters in diameter can be very destructive to spacecraft, and they can actually stay in this orbit for long periods of time. But it's really only the objects that are above 50 centimeters where we obtain good constraints, good TLEs, which are the 2-line elements. But for the objects below 50 centimeters, we just have sporadic observations. And so we use the 2.5 meter telescope, the Isaac Newton telescope, to help track some of this debris. And so here's a brightness histogram of some of these results. The blue histograms here are correlated with of objects that are actually seen, actually known. But what's more concerning of all of the red histograms that you see here, these are objects that are uncorrelated, that we can't associate with a particularly known object. But our observing program shows quite a number of these, up to about 10 centimeters. It goes up to 21 in terms of visual magnitude. So that's where we cut off. This histogram probably goes up further. And we obtained this 10 centimeter estimate by assuming Lambertian spheres and also an albedo of 0.1, but that's very uncertain. And here's just a taste of some of the light curves that we have. This is the y-axis here represents the magnitude, the V magnitude, and the x-axis is the time difference in seconds. So you can see in the bottom right panels, there's a 5 to 6 order of magnitude difference over just 10, maybe 20 seconds. And so in some of these cases, and those represent effectively glints. So maybe these debris is actually tumbling that's just beyond our magnitude limit. And finally, we've recently supplemented our 2.5 meter observations with commercial off-the-shelf components. This is a 36 centimeter astrograph, and this just shows you some 10 to 12 minute arc detections. These are useful supplements because these provide a wider field of view than the 2.5 meter observations. So with that, this is my final slide. I just wanted to conclude by saying I think there is this relation between stardust and exosystems through asteroids and dynamics. And so thanks very much for your attention.